Last episode, we turned a corpus into vectors and a query into a vector and found the right passage by cosine, but I ended on the catch. I compared the query to every vector. Over millions, that's hopeless. You need an index, a smart structure that finds the nearest neighbors without looking at all of them. And on this course, ideally one that runs on the GPU. Exact search compares to every point, perfect recall, but order and dead slow at scale. So we go approximate. Approximate nearest neighbor accepts a tiny recall hit and skips most of the vectors. There are exactly 3 ways to skip work, and every index is one of them or a combination. Way 1. Clustering. IVF runs k-means to group the vectors into cells, and at query time it only searches the cells nearest the query. The dial is nemprobe, how many cells you check. Crank and probe up, recall goes up, and so does latency. The number of cells and list is roughly the square root of your vector count. Way 2. A graph. HNSW builds a multi-layer small world graph and greedily hops from an entry point toward the answer. Order log n, blazing fast, but it eats memory because you store the graph on top of the vectors. It's the modern default for low latency online search. Way 3. Compression. Product quantization chops each vector into subpieces and replaces each with a codebook ID. Tiny memory, a little lossy. For billions of vectors under limited RAM, you combine them, IVF plus PQ. Now the databases. FAS is a library, not a server, 20 plus index types, the fastest raw indexing, GPU support, you embed it in your own process. Milvus is the distributed production scale one, and it was the first vector DB with GPU Kagra indexing. Kubernetes Rust HNSW with great metadata filtering. Chroma is HNSW only and perfect for prototyping. And the NVIDIA differentiator, Kuves and Kagra, put the index itself on the GPU. Kagra is a graph index built for GPUs from scratch, reported up to 12 times faster builds, and Milvus up to 50 times faster search versus CPU. Let me lay out the 4 index families as cards, each with a glyph for how it works, and arrows for memory, recall, and speed. Then the database picker and the GPU callout. Card 1, flat, a grid where the query compares to every cell. Recall arrow maxed, it's exact. Speed arrow at the bottom. Order n. Memory full, this is your ground truth baseline. Card 2, IVF, a Voronoi diagram of cells. The query lands and only mprobe nearby cells light up and get scanned. The mprobe slider trades recall for latency. Card 3, ChansaW, a layered graph, entry at the top, greedy hops down to the answer. Order log n, the speed arrow near max, but the memory arrow is high. Card 4, PQ, a vector split into sub-blocks mapped to a tiny codebook. The memory arrow tiny, recall arrow slightly down because it's lossy. And the composite IVF plus PQ for billion scale. The database strip, prototype reach for Chroma, single service with good filtering, Qdrant, massive scale and distributed Milvus, library level, embedded in your own code FIs. Now the GPU callout lights up green, QVS plugs into face and Milvus, and Kagra is the GPU native graph index. The index runs on the GPU, not just the embedder. So we can store millions of vectors and find the nearest ones fast on the GPU, but pure vector search has a blind spot. It's great at meaning and weak at exact terms, like product codes and rare names. And the top K it returns is only roughly ordered. Next, 2-stage retrieval, hybrid search, rank fusion, and re-ranking. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.